Hey, welcome to my video on a series RLC circuit. So we're going to perform some calculations on this circuit above. We're going to focus mainly on using Pythagorean's theorem as well as a little bit of trigonometry and a phasor diagram to analyze the phase relationships. So what we have here is a series RLC circuit. So just kind of pretending that it's going to come back around to the source, giving us that series circuit. In this circuit, we see a 240 volt source, 10 ohm resistor, 350 microfarad capacitor, as well as a coil with both a resistive component and an inductive component. The resistive component is 3 ohms, the inductive component is 45 millihenries. So when we look at a circuit like this, just like all circuits, right, I like to just break it down into the individual components, right? So first of all, our 10 ohm resistor, well, it's already broken down into ohms. It's just 10 ohms. Then we have our 350 microfarad capacitor. So with microfarads, we want to turn that into an ohmic value. And with a capacitor, we get capacitive reactance. And we know the formula for that is 1 over 2 times pi times frequency times capacitance. So remembering to convert capacitance into farads instead of microfarads, so moving that decimal place 6 places. But in this case, we end up with 7.579 ohms. So that's our capacitive reactance, or our reactance due to capacitance in this circuit. Then over here, we're already given the ohmic value for our resistance. We want to do the same thing here. We want to get our inductive reactance, or our XL, and the formula for that is 2 times pi times frequency times inductance. So again, turning the millihenries into henries, moving that decimal place 3 places, but we end up with 16.965 ohms. That's our inductive reactance. Now I want to break it down just a little bit further, right? This is just one component. This is just one component. We really have 2 things going on inside this coil. We have a resistive component, which is always a horizontal value, and we have a vertical value, which is our inductive reactance, 16.965 ohms. So that's what we have going on inside that coil. Now, this again is just for our coil, but we can solve for the angle of the coil as well as the impedance of the coil. So in order to solve for the impedance of the coil, what we're going to use is Pythagorean's theorem. We're going to go Z of the coil equals resistance squared plus the XL squared. Punch that into our calculator, and in this case we end up with 17.228 ohms. 17.228 ohms. Now the last thing we can solve for is going to be the angle of the coil. Now lots of different ways to solve for the angle, any one of our trigonomic functions, right? SOHCAHTOA. I'm going to use cosine in this. So I'm going to get theta equals arc cos adjacent over hypotenuse, which would be arc cos 3 divided by 17.228. In this case, it's going to give me an angle of 79.97 degrees. That is my phase angle just for the coil. So again, you can use any trigonomic function. Cos is my favorite. We get that 79.97 degrees. Punch that in here, 79.97 degrees. Now that would be a lagging angle, right? And we'll talk about that as we talk about the phasor diagram. So now what I want to do, now that I've broken down each component in to get their ohmic values, I want to get the total circuit impedance. My goal at the end of this video is just to get my current. So I'm going to break it down, get my total circuit impedance. So what I see is something like this, and I'm going to do that over here. I know in series, ohms of resistance add up directly. So I know I have 10 ohms is my resistor plus 3 ohms of resistance inside my coil. Those are going to add up, which at the end of the day, that's going to give me my R total of 13 ohms. And that's a horizontal value. Plus I had my inductive reactance of my coil, which my XL was 16.965 ohms. And I have my capacitive reactance, which was, if I remember correctly, 7.579 ohms. So I arrange all my information in an impedance diagram like this. I can see everything all together. Now, what we need to know about XL and XC is they occur 180 degrees apart, which means they cancel each other out. So because I have 16.965 ohms of XL and 7.579 ohms of XC, we get an X net, or a net reactance. They cancel each other out. So whether you want to go XL minus XC, that works out okay. At the end of the day, in this, we get an X net of 9.386 ohms. So those are going to cancel each other out. And I don't want to write myself off the board here, but that's going to go onto our circuit impedance. This is Z of the whole circuit right there. We got an X of 9.386 ohms. Now again, what we're going to do here is we're going to do Pythagorean's theorem to get the Z of the circuit. So we take our X net squared plus our resistance squared, and we square root the whole thing. Same formula as over here, right? So it's going to be Z total equals R total squared plus X total squared, square root the whole thing, which is going to give us, in this question or in this circuit, a Z total of 16.034 ohms. Now, what we can do with that information, what we like about that information, is I can get my total circuit current. And I'm just going to use Ohm's law for that. I know that current is directly proportional to voltage and inversely proportional to the opposition. So I'm going to go I equals E over Z total, right? My total current over my total impedance. So I'm going to do that, which I go to 240 volts divided by 16.034 ohms. Gives me the number I'm looking for. It gives me 14.968 amps. And that is how I would solve for total current in a series RLC circuit. What's really important about that, what I like about that current value, is that I can take that value, 14.968, I know that that current is through the entire circuit. 14.968 amps. I know that flows through the resistor, it flows through the capacitor, and it flows through the inductor. Okay, so now what I want to do, I'm going to clean the board, but then we are going to talk about the phase relationship between all the voltages and all the currents on a phasor diagram. So stick around, I'll clean this board off, and we can get going. Okay, so we're back. Now, I erased a little bit of info here, but let's just remember our XC was 7.579 ohms. And over here, we had a little impedance triangle, looked like this. Our R was 3 ohms. Our XC was 16.965 ohms. Our Z was 17.228 ohms. And our angle was 79.97 degrees. It's just a quick refresher of the info that we had. So what I want to talk about now is I want to talk about the voltages and the voltage relationships in this circuit. Now, we have 3 different voltage drops. We have a voltage drop across the resistor, a voltage drop across the capacitor, and a voltage drop across the inductor. Now, the big thing to remember with the voltage drop across the inductor, it is across both the resistive component and the inductive component. Okay, so it's across both of them. When we pull out our meter, we're going to only be able to meter the whole thing. We can't meter individual components, okay? So we're going to take all this information and we are going to plunk it onto a phasor diagram. So let's build one of those real quick. All right. So how this works in a series circuit, in our case, because we only have one current, we're going to use our current as a reference, and we're going to base everything off of that. So this will get a little bit tricky, but that's okay. So we have our current with our closed arrowhead. That's our I total. So now let's do the individual components. So talking about our resistor, if we're going to figure out the voltage drop across our resistor, we're simply going to use Ohm's law. So across the resistor, I would take the current flowing through my resistor times the resistance of my resistor, and that's going to give me a voltage drop. So in this case, it gives me my voltage of my resistor. I'm going to put that right here. Equals 149.68 volts. So that's my voltage drop across my resistor, VR. Right, and again, I'm just using Ohm's law to calculate that. So I'm really just going, voltage equals current times ohms, okay? Now we'll do our capacitor. So with the capacitor, I want to use the current flowing through the capacitor and the ohmic value of that capacitor. So I'm going to go 14.968 amps times 7.579. That gives me my V of my cap. Again, that would be measuring from here to here. My V of my cap ends up equaling 113.442 volts. The last one I'm going to do is the voltage across my coil. And again, my voltage in my coil, remembering it's based on the whole coil. So we have to use the impedance of the coil. Okay, we want to use the impedance because it's all part of the coil. So I take my 14.968 amps times the impedance, 17.228 ohms, gives me my V of my coil. In this case, it gives me 257.869 volts. Yes, it's not a mistake. You can have a voltage drop across a load greater than my source voltage, which is crazy. We know that in a series circuit, my volts total, or my E total, is V1 plus V2 plus V3. How can that be? It's because they're all occurring at slightly different times. So we know, and this is something that as electricians is very important to us, a voltage drop across a resistor, the current and the voltage will be in phase with each other, okay? Which means that this voltage drop, because our current is our reference here at 0 degrees, this voltage drop also occurs at 0 degrees. So when we punch that on here, we're going to say, okay, it is also occurring at the exact same time. We'll call this my VR. Awesome. Now let's talk about the capacitor. So the voltage drop across my capacitor. A capacitor or capacitance opposes a change in voltage. If I'm opposing the voltage, that causes my current to lead. So you could say across a capacitor, the current will lead the voltage by 90 degrees. Okay, so if the current leads the voltage by 90 degrees, my current is here on the reference. That means my voltage is actually down here, V cap. My voltage is lagging my current by 90, or my current is leading my voltage by 90 degrees. So that puts this actually at 270 degrees, or you could say at negative 90 degrees, whichever works for you. Now my coil is the tricky one. So because my coil has a resistive component and a reactive component, I'm going to have some in-phase voltage across the resistance and some out-of-phase voltage across that reactance. So we have to use that same angle. So in this case, because inductance opposes a change in current, it causes my current to lag. If my current is here, that means my voltage is going to be up here with my current lagging behind. And it's going to be by the same angle as your ohmic value. So in that case, 79.97. That's going to put my V coil up here at that 79.97 degrees. Now what we do with this information, we are going to add up these voltages, V1 plus V2 plus V3. We're going to add them up vectorially. And we're going to do so, in this case, using what we call an HV chart. So because it's like solving a triangle, every time we solve for H, we're going to use the cosine function. And every time we do V, we're going to use the sine function. Now I have a couple of videos on adding phasors, and you can check those out in the description below. So I'm just going to do this math up real quick. All right, so once we break those down into their horizontal and their vertical components, now what we do is we add up all the horizontal components. So 149.68 plus 44.907 gives me a total of 194.587. Do the same with vertical. Negative 113 plus positive 253 gives us 140.487. Awesome, so we add them all up. What this does for us is this actually creates a little voltage triangle. So I like to just sketch it out real quick, just like that, just so I have a representation that I can see. Got 194.587 and 140.487. This just gives me a visual representation of where that total is going to be. Then what we do, we use Pythagorean's theorem again. We take our total horizontal squared plus our total vertical squared, and we square root the whole thing. Again, Pythagorean's theorem, that gives us a total. In this case, we'll call that E, total. And we end up with 240-ish, really close, 240 volts. And that's exactly what we were given to start with. So we've really just confirmed that all the work we've done along the way is correct. Now what's really important here is that angle. And we call this our circuit phase angle. The phase angle is the angle between total current and what we're going to say is their total voltage. So I'm going to use any trigonomic function and I'm going to solve that angle. In this case, I like tan. So I'm going to go theta equals arctan opposite over adjacent. Right? So I'm going to go arctan, opposite being 140.487, divided by 194.587, putting that in brackets. This gives me a phase angle of 35.8 degrees. Now that's exactly where my phasor goes onto my phasor diagram. So 35 degrees is about here. 240 is about that long. That's my E total. Now that's that, right? All we're doing is we're taking those three phasors and adding them together. Now this isn't going to work out perfectly, but it'd be like if I took this phasor and added it to this phasor, and then added this phasor to it, which brings me back down here. Again, mine is not to scale, so it's a terrible representation, but you can do that tip to tail method as well. So I really hope this helped. Thank you so much for watching. This is a series RLC circuit. What we did is we took it from those base ohmic values, we found our total current, and then we found all our voltage drops within the circuit. Using those values, of course, we could find the powers, both true power and reactive power at all the components, but we're not going to do that today. So thank you so much for watching. I have a couple more videos linked below that might help you out, and have an awesome day.